You ready? I think Mr. Akasha, I cannot hear your voice. Mr. Akasha is quite low. The voice is in a low volume.
Maybe my internet connection is not so good, Doctor.
Yeah, but it sounds better now.
Oh, okay, I'll try again.
All right.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين يجوز نعمه ويكافئ مزيدا يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على محمد وعلى آل محمد اللهم اغفر لنا ذنوبنا لوالدينا وارحمهما كما ربنا صغيرا اللهم اجعلني
واجعلني في قلبي نورا وفي لساني نورا وفي بصري نورا
في سمعي
وفي سمعي نورا وعن يميني نورا وعن يساري نورا ومن فوقي نورا ومن تحتي نورا ومن أمامي نورا ومن خلفي نورا واجعل لي في نفسي نورا رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم الراحمين.
سبحانك ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin amin ya rabbal alamin. Thank you so much to Mr. Akasha for the pembuka and penutup, and thank you to everyone for reciting the doa. So without further ado, we will start our class. As you can see from the agenda of today's meeting, I'll just like to brief a little bit what we will be doing today. We will continue our class with topic 2 until it finishes for topic 2 in week 2, lesson 2. Then when we have enough time, hopefully if we have enough time, because the aircon is not so cool, but anyway, if we have enough time, then we will go to our breakout rooms, and I give you options for you to try out during the breakout rooms, either trying the kinetic challenge, which you can have an access through that website link from Michigan University, where Professor Fogler is working. And the second option would be make a discussion on question H and I, which you can read from the textbook at the end of the chapter. I didn't write it. Chapter 5, yeah? At the end of chapter 5 in Fogler textbook, there are two questions that I think are quite relevant to what we will be doing today, which are question H and I, so you can make that discussion, yeah? If you choose option number 2, then you can try out the kinetic challenge at any other time at your own pace, yeah, at home, okay? It may take some time to do that, because it's either you compete with your friends or you can do it alone. Yeah, I think it's competing with the computer thing. I'm not so sure. Yeah. So have a look with that kinetic challenge. Yeah. Then we will start right away with our lecture. And when I start my lecture, you can switch off your camera. Thank you so much for your cooperation. All right, so I will start sharing my lecture notes. And you have already obtained the lecture notes from our previous lesson 2, week 2 in PDF form. But the few remaining contents I haven't shared, yeah, in that PDF. But you can see it today, yeah, not so critical, but yeah, I hope you try to take notes. And from the previous contents, I also made some corrections. I don't remember where, but please take note, yeah, from the screen. and also from your PDF if you have both printed. If you have the other one printed, okay? If not, just focus on the slide that I will be sharing. Can you see my PowerPoint slide already?
Yes.
Yes. All right, very good. So I am going to scroll down and you see it's moving, right?
Yes, doctor.
Very good. I think we stop until here. That was the last slide that we did together. And this is class K. Or maybe we have touched a little bit on here already, right?
Yes.
Yeah, very good. So yeah, thank you, Adriana. In any way, I will refresh back what we have done, starting from part batch reactor analysis in topic 2. Okay, so as we know that we need to analyze the data from the experiments in the lab. And the data acquisition can be in the form of concentration versus time. As you know that you will collect the data, the concentration of the reactant at varying time by using your batch reactor. Yeah, the experiment was done in your batch reactor. And the data collected is based on transient time, meaning at varying time, different time. Um, there are also means to run your experiment in steady state in the differential reactor. But in this topic, we were still focusing on the assumption of constant volume, yeah, in batch reactor. On your right hand side, the few ways that you can adopt to determine your K, your rate loss, either first order or second order or third order depending on the order of the reactions, which is the N if you are referring to the overall order. With respect to a component, it can be, let's say, 2 A plus B, then produces C plus D. And this is something else, yeah? Something else. Um, it depends on the K, C, A to the power of A, C, B to the power of B, for example. So with respect to A, it can be that A order, the small a, or with respect to B, the component B can be in B order. Or sometimes I write C A alpha, C B beta. Yeah, it can be alpha order for with respect to A, or it can be beta order with respect to reactant B. All right, to do that, we can analyze the data that you have collected from data acquisition, yeah, either by adopting integral method or differential method, initial rates method or half-lives method, or last one would be least square analysis by using software. The easiest would be the integral method, and the second one would be the differential method. That the rest of the other two methods will be touched not so much in detail, but it will just be an introduction to you. So we let's bear in mind we would like to know what is the difference between integral method and the differential method. Since I wrote integral method as the first method here on the slide, I will go to my next slide introducing you just to make an introduction. How does integral method looks like? Yeah, let's go to this integral method. Okay, the integral method is simply by writing the formulas that are related. yeah, from that formulas, we are able to determine whether it's zero, first or third order. But there is a rule for that. Yeah, if you assume it's zero order, if you get a straight line, then it's proven that it's zero order. So the same thing goes to first order and uh, the third order. Yeah. So that would be integral method. We will come back to that later. But now I am going to start with the differential method. I'm going back to our previous slide. Right? Before doing that, so we want to ask ourselves why we want to analyze this data. Because as you know, we want to know the reaction order and also the specific rate constant. There are few steps for you to follow by first postulating your rate law, determining which reactor type, and write your mole balance based on your reactor type. If it's batch, then you write the mole balance based on batch. Then you process the data based on the measured variable. In this case, you measure concentration of reactant A, then your measured variable will be CA. Out of the uh, rate, rate reaction equation, you can make certain simplification based on the assumption either the reactant is in excess or limiting. All right, so this is simply to simplify the equation so that we can easily analyze the data based on the simplified equation. Finally, solving the equation, you will be able to know the reaction order and the specific rate constant, either by using the integral method or the differential method. Now, I think you have seen this as well. This is just refreshing, either homogeneous or heterogeneous. Of course, with the heterogeneous, maybe you have catalyst here with the solid form, and the homogeneous, if it's unimolecular or bimolecular. Yeah, these are just an example. So we also have three molecules. Yeah, this is just one of the example. So please take note that if you see this unimolecular reaction, the A simply produces C, then this is how you write the rate of reaction, yeah, with the rate constant, which is the temperature dependent term multiplied by the concentration dependent term, which is the concentration of the reactant to the power of the stoichiometric. Yeah, in this case, it uses alpha, so don't get confused. Yeah, in my lecture, sometimes I write ABC, sometimes I write alpha, beta. Okay. Same goes to here. We have bimolecular. So you write the rate, the temperature dependent term, which is the rate constant, and the multiplication of the two reactants. Yeah, Ca to the power of alpha and Cb to the power of beta. Okay, it follows the power law model. So the reactions are written based on the power law model. If it's heterogeneous, it follows Langmuir-Hinshelwood model. For example, here, basically mainly for the example of gas solid, the solid comes from the catalyst and the gas could be the reactants and the product. So due to gas, so how are we going to quantify or express the change of concentration during the reaction? Simply by expressing the partial pressure, yeah. Normally, okay, I think I should write it as small p, yeah, italic, yeah. This is a little bit confusing. If I write it capital P, yeah, take note, yeah. But it's okay if you define it as a partial pressure, okay. So note that the concentration of the gas expressed, the concentration of the gases are expressed based on the partial pressure. Then we have the rate constant, then we have the adsorption constant, for example, since we are dealing with the solid. Um, now, the second step is to choose your reactor. So we chose batch reactor with certain assumption. whereby the constant volume of the reaction mixture is assumed. And sometimes, to make it much easier, you also let the temperature to also be constant. So it's an isothermal reaction. Yeah, this is an extra assumptions which I want to express uh, on this slide. Yeah, but you will see later in our future slides when we do our analysis of the data collected on the experiments that we conduct. Okay, so based on the batch reactor, the change of the rate of reaction, so this is the rate of disappearance of the component A, reactant A, because we have negative, is simply the change of the concentration of A per unit time. Yeah, take note that we have negative here. So the question would be, how do we get this question? This equation. If you could still remember, we did that in our previous lecture. So we can go back to our previous lecture, how we derive that equation, yeah? The rate, that equation. I think we did derive that somewhere. If anyone has your slide with you, you can just tell me at which number of the slide. But I think it's somewhere. Just want to go back so that you can remember, yeah, because you will be seeing lots of equation today. So I don't want you to get so overwhelmed until you don't know what you learn till the end of my class today, yeah. So we'll go back. We have that. Tak jumpa pula. Ada siapa-siapa nampak? Oh, laju je saya pergi depan. Sekejap ya. Somewhere around here.
Slide 80.
10 ya. Thank you, Afsar. Hold on. All right. So slide 80. This is where we derive our rate of reaction, yeah, in a batch reactor with the assumption of constant volume and also constant temperature. So please take note, this slide is very important. When we know that the rate of reaction in a batch reactor at a constant temperature and constant volume is simply the change of the reactant per unit time. And that, of course, is equivalent to the power law equation that we assume. Yeah, we write based on the reaction equation. The A produces product. All right, so we're going to go forward. Back. Not so much behind. Thank you, Mr. Afsar. All right, so now the step 3 would be process your data. Yeah, you have already your principles, you understand the theory. So we are going to process our data, which you collected during the experiment, based on the measured variable. Here, the measured variable is the concentration of your reactant A. If it's gas solid, then when necessary, if it's gas solid, yeah, then you express your data based on the concentration of the gas, which is the partial pressure. So it depends on how you collect the data. So if you have in your reactor, the A produces C, for example, then the A, if it's liquid, then homogeneous liquid, the measured variable, you take your data through different time, is simply the concentration of the A. But if you have your reactor with the solid, this is liquid, then solid, or the gas, then the gas concentration collection of data would be your partial pressure of the A. Yeah, partial pressure. All right. So you process your data based on your measured variable in your laboratory, yeah, during the experiments. Okay. So step number 4, once you know your measured variable, of course, we will write our mole balance here according to the batch reactor system. Based on your measured variable, which is CA, for example, it could be the partial pressure. So this is the thing that I said I updated my slide, okay? When I wrote the first time, that is what I think everyone can understand, yeah, from the English sentence. So I try to rewrite it in a clearer sentence. Yeah, please take note in your PDF form. So please write it on your own. Then step number 4, having that mole balance equation, we want to simplify the equation by our assumptions. If one of the reactants are in excess, yeah, if one of the reactants, if one is in excess, because we are talking about one, assume its concentration is constant. So we will see on how to do that, yeah, when we do this assumption, yeah, how we simplify that equation. So basically, these are the steps that you want to bear in mind when we start analyzing the data that you obtain from the experiments. So the last step would be determining the reaction order and the specific rate constant. The reaction order is the N, the specific rate constant is the K. So this is what happens, yeah? You collect your data, you have your concentration versus time, okay? Then we want to write our equation. Yeah, we start to write our equation. Having said that we have A produces B, for example, yeah, only unimolecular. The first scenario of writing the equation according to the power law, the rate of disappearance of the reactant A is simply the rate constant A, we simply refer to A with respect to A, times the concentration of the A to the power of alpha, right? Now we don't know what alpha is, yeah? We don't know, yeah? We don't know yet. So, but we write theoretically based on the power law model. Then the second scenario is we know that the rate of the disappearance of A, based on our understanding, it's simply the change of the concentration of A per unit time. So you write that equation and you relate equation 1 and 2, knowing that that is your equation. Yeah, the change of the concentration per unit of the reactant A per unit time is simply equivalent to minus Ka, which is the rate constant of the component A, rate constant with respect to reactant A, times the Ca to the power of alpha. All right. So having that equation, so we are now at step number 2 here. Plot, yeah, of course, from here to allow allow simple analysis, we would rather have, we have to vision this mathematically, we would rather have a straight line so that we can have y equals to mx plus c, linear equation, yeah? Because when we have this linear equation, it will be easier when we know the intersection from the graph, which is the intercept, the c, and you know the slope. By having this equation, it is not a linear line. So in order to create linear line, simply take natural log from both sides. So this is what happens. You make both sides left and right ln, yeah, logarithmic, natural log, logarithmic e. Then from here, the nature of this equation now becomes a linear equation. So from here, we can identify that the ln minus dCA over dt is simply the y-axis, which is the y-axis here. And the alpha is simply the slope. So the slope here is alpha. So once you know your slope, then you can know your overall reaction order. So the C, which is the intercept, is now the ln K. What is K? K is the rate constant. So once you know your C, and C is equivalent to the ln K, then you can know your rate constant, which is K. All right. So that is the idea of doing this. So the step 3 says we can find our K from the intercept. Yeah. So this is what we mentioned just now. And we can find our reaction order from the slope, which is the M. All right. Now, to help us to do all this, there are 3 methods that we can choose, either one by proving using graphical method, which is this one, graphical method, or numerical method. So we will use calculations, yeah, based on finite difference equations. I'm not sure whether you have learned your numerical. I think you took that last semester, right? Numerical class.
Just like that.
Yes, very good. And the last one would be the integral method. Yeah, okay. So we will go one by one. Of course, the one that I showed just now, this one, which I circling, is the graphical method. So let us start one by one. These are all these overall, we call it differential method. If we go back to our previous slide, we have this integral method, then differential method to help us find our K and N. The differential method can be categorized by the graphical method or the numerical. Numerical, we use the numerical equation to find our data. Yeah, you will see that in a minute, right? Now, so let us start with the first one. Assuming, as you know, that we ran our experiment in isothermal condition and also constant volume batch reactor. Here would be the equation that you derive from our previous slide, which is this one, yeah? Ln minus dCA over dt is equivalent to ln K plus alpha ln Ca. So we should expect that our x-axis is the ln Ca logarithmic value, and our y is that. So this is what you see, yeah? The y is the minus dCA over dt. The x is simply the concentration of the A. And the data are plotted in a log graph. You can do that manually or you can do that in Excel, all right? In Excel, Microsoft Excel. Both are in log. Have you heard of the log graph? Okay, the simple y and x axis, which is, let's say, 1 here, the scale 1, 1, 2, 2 with the same scale, yeah, the same scale. This is a normal graph. This is not even logarithmic graph, right? So we may have y and x axis. Let's say this is logarithmic. This is not, then this is what we call a semi-log graph. Semi-log. This one, since we have log, then we call it log graph. Yeah. So simply like 10 to the power of 2 is 100. So how do you re-express this in terms of logarithmic? How do you do that? How do you express this into logarithmic? Siapa tahu? Ingat tak? Tak tahu lah ni subjek bila punya ni. Siapa nak cuba? Mari kita tengok nama, tengok. Tu yang duk buat habis lambat tu. Duk sibuk cari. Siapa saya nak tanya soalan? Ha, nak tanya siapa hari ni? Oi, sukalah nama ni. Sebab dia selalu jawab sebelum kelas ni. Nada. Nada.
Nada pergi tandas.
Miss Nada. Apa dia?
Nada pergi tandas sekejap.
Saya baru nak cakap, Nada mesti sibuk tanya Syafiqah. Tiba-tiba Syafiqah yang jawab. Okey, Syafiqah jawab. You sehati sejiwa, Nada tak boleh jawab, Syafiqah jawab. Tapi kalau midterm assessment tak boleh lah share-share jawapan. Berdosa. Unethical. So, Syafiqah. So, how do we convert this into logarithmic form? Ni matematik, tak tahulah. Kata satu kot. The keyword is log. So, macam mana nak buat? Mesti Nada tak nak keluar tandas ni. Nanti saya kena tanya dia, dia kena jawab. Okay, Nurul Ashikin. Nurul Ashikin. Okay. Semua diam je. Semua kita anda agaknya. Mirza. Mirza. Daniel. Daniel. Yang lain-lain tu carilah jawapan. Nanti turn kamu saya panggil boleh jawab. Fazlika. Raja. Yes, Mr. Raja. Where are you?
Ada, Doktor.
Okay, so how do we convert this into logarithmic equation? Macam mana tu nak buat?
Log both sides.
No. Tiba-tiba ya je. Terbantuk Raja nak jawab. Okay, teruskan. Log both sides. Okay. Boleh ke?
Tak sure.
Kata satu Raja.
Syafiq kata dia tahu.
Afsar lah, Afsar. Siapa tahu? Siapa kata tahu?
Syafiq.
Oh, Syafiq. Okay, saya nak letak rule lah. Siapa saya panggil nama je, dia kena buka video. Saya tengok muka dia. Dia tengah fikir ke? Dia tengah buat apa? Syafiq. Mr. Syafiq. Satu rumah Raja dan Syafiq. Ni yang hari tu masa mula-mula kamu share komputer kan?
Masih share, Doktor.
Share video. Share kamera, ha? Siapa jawab? Saya tanya Akashah lah. Akashah. Mana Akashah?
Just log 100, Doktor.
Yes. So, please continue. Log.
Log 100. And then equal to 2.
Equals to?
2.
Yeah. All right. So when we do our log scale, I would like to assign you to go to do some searching. How does it look like for a log graph? Because this is a principle of your logarithmic, yeah. It may not have. So please describe your log graph. How does it look like? So for a normal graph, when we have a standardized scale, yeah, it's a 1, 1, 1, 1, 1. So what about the log scale, yeah, the log scale? So please do that, yeah? because you are not only going to solve this by using the equations that you have derived. It's very spectacular. You can find the K and also the overall order, but using the log-log graph, if you don't know what it means, then something is wrong, ya. To solve that, kalau dalam exam mungkin disuruh buat graph, then you have to know how to plot your graph, ya, using a log-log graph. Then you have to know that there is such log-log graph. Then you have to find it. So have a look. How does it look like? Kata you pergi kedai stationery, tengok ni graph. Alamak, mana satu graph, buat balik salah graph. Rupa-rupanya buat balik normal graph, but you need the log-log graph, for example, or semi-log graph, or you can print it. So how to print it? Yeah, search for it. All right. Thank you, Ms. Akasha. So we are still here by plotting at log-log graph for the CA in the x-axis and the change of temperature per unit time negative. You can get a linear curve. So this is what it means by deriving such equation. Yeah, from that equation, then you can solve for your slope. This is slope. And you can solve for your C, yeah, intercept. Okay, from there you can find your alpha and also your K. Now, how to find the value of the rate constant K? Okay, the first one, of course, you can find the K from the C, or you can alternatively adopt this method by choosing at any concentration, yeah, for a certain pressure. If it's partial pressure, then simply get the derivatives of that concentration at that particular point. And to find K simply by using this equation, which is the derivatives, negative derivatives of the particular point, concentration A, per the concentration of the reactant to the power of alpha, right? Of course, you have to know your alpha first, then only you can solve for your K. You can also adopt this method, or you can simply adopt this method by determining the intercept. Yeah, I would rather go for this method. Yeah. Now, so let us look at one of the example of the triphenyl methyl chloride, which is the reactant. A reacts with methanol, B. So we have this methanol as B, and your A, reactant A, producing C and also D. So we have this collection of data in your lab, whereby at varying time, initial time, T0, 50 minutes, 100 minutes until 300 minutes, yeah, with a specific or custom range of 50 minutes. So take note that we have 50 minutes range. So every 50 minutes you start to collect your data, and the collected data based on the concentration of A is 50. Yeah. So please take note, yeah, when you do your experiments, you measure your reactant A. So you get the value in terms of mole per decimeter, cubic decimeter, right? So I hope that you know how to read this table. All right. Now, can anyone please tell me what is the concentration of A at 200 minutes? Anyone? From that table. Okay, so what is the concentration of A? Just tell me. So we have this unit there, at time 200 minutes. But what about the concentration of A? Anyone? Tadi Nur Nada dah keluar tandas dah? Nur Nada?
Dah.
Yes, Nur Nada? Dah. Okay, so what is the concentration of A at 200 minutes?
22.2 times 10 to the power of 3.
Oh, okay. Nonada, kita tanya Syafiqah. Nonada jawab betul ke? Baca table pun kena tahu juga Tiba-tiba orang yang buat eksperimen tu orang lain. Dia tulis tiba-tiba you baca salah. Ni betul ke tidak ni?
10 to the power of negative
Syafiqah.
P.
Mr. Afsar kot. Mr. Afsar. 10 to the power of minus 3. Alright. Boleh cerita tak kenapa? Afsar.
Satu sebab
Mr. Afsar?
selalunya table memang dia tak letak negatif tu. Tapi satu lagi dekat bawah tu ada clue. CA705 mol. Bila kosong.
Tak, yang ni bukan clue dia. Ini clue untuk initial time. Initial time or start time. So this is the initial concentration. Janganlah teka by clue macam tu je. Tak boleh. Kena berdasarkan pemahaman. Okay. Siapa yang kelas saya last semester? Mr. Akasha. Mesti dia ingat. Ada kot last semester. Ada kot. Ada saya rasa. When you read your appendix.
I don't remember, Doktor.
Okay, Akasha. Alah, tak ingat pula. Aduh. Very easy ya. So kat sini tengok ya. So please take note ya. It's very important ya. You kan engineer. Kerja-kerja buat eksperimen ni bukan you. Okay. Tapi kalau you lah. Orang lain, saintis. Dia dah buat eksperimen, dia dah collect data pun a very good table. Then give it to you, tiba-tiba you baca salah. Alamak, malu. Betul tak? Betul ke Afsar? Betul Nada kan malu dapat degree penat-penat yang buat saintis tu. Bukan degree ke kata ke, tiba-tiba you silap pula. Alah, rupanya salah. Silap je sebab tersilap. So based on how you write your table, ya. For example here kat sini says there CA times 10 to the power of 3. Okay, kita mula dengan T Okay. T time is 0 minute. Betul? Time lah. But the second row is CA times 10 to the power of 3 is equivalent to 200 minit kat sini. 22.2 mole per cubic dm cube, cubic decimeter. So CA is simply you bring left to right lah. So 22.2 times 10 to the power of minus 3. So is it clearer now, Mr. Afsar?
Yes.
Right? Okay. Mr. Akasha? Nonada? Syafiqah, Azri, Dania, Kamelia, tak tahulah semua gimana. Atrisha, Anis, Amira, Nazrin. Okay, right. So now, where are we now? We are going to plot this concentration versus time. First, of course, following the steps, postulate the rate law using if it's homogeneous, then you use your power law. Then you have A plus B produces C plus D. Your reactants are two reactants. So you have 2 multiplication of the concentration dependent terms with that rate constant. Okay, you do of course, this is from batch reactor. And you want to process the data collected based on the concentration of the reactants. Now, from your experiments, the concentration of B is 10 times in excess, 10 times, yeah? So you have your reactor, you know that you have A, B, and then through time you put nampak ada C and D, yeah? So those are your products. But from the concentration of A and the concentration of B, you can know from your sampling that one of it is either excess or limiting. In this case, let's say if the A is limiting, the concentration of B is way higher than the A, all right? 10 times. then you can say it's in excess. 10 times 2 is just an example, meaning way, way higher from the A. Of course, through time, your CA and CB through time, time T1, time T2, time T3, CA1, blah, 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 CB1, blah, 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 blah. Of course, as time increases, the CA, of course, decreases. Your CB, of course, decreases. So take note, this is irreversible. Ya, dia tak pergi patah balik. So the reactance decreases. But the CB, walaupun dia decreases, tak banyak. Ya, dia in excess. Dia guna, tapi dia banyak sangat. Macam tidak memberi apa-apa effect. Right? So we can say the concentration of B is in excess. Yeah, and to make a simplified equation for that, to simplify your power law equation tadi from our previous slide, this one, step number 1, we write the CB, of course, is equivalent to the CBO, macam tak memberi kesan apa-apa. Alright, ibarat macam at any time the concentration of B tu macam mula-mula dia masuk, something like. So this is how you write the equation. So therefore, from your power law equation, you have this case KCA alpha, CB beta. Simply, the CB beta is your CB naught, right? And the simplification that you can say here is as if this is constant, ya, constant, macam tidak memberi kesan apa-apa. Therefore, the rate of the disappearance of the reactant A is simplified as K prime Ca alpha, right? Saying K prime is actually K Cb naught beta, right? So this is an assumption that you want to use for the simplification step, yes, step number 4. Okay, so the rate of disappearance of A is equivalent to K prime Ca alpha, and that prime meaning ada K dan Cb not beta there, right? So we don't consider that lah in this change of concentration because kita kata ibarat dia constant, tidak berubah because of the excess concentration. Okay, do you have any question? Okay, because this is important, yeah. You'll see in, yes,
Nak tanya.
yes.
Yang apa tu nama tadi doktor kata yang kena ada assumption yang kalau 10 times apa concentration of B is 10 times the initial concentration of A, tu memang kita guna untuk semua reaction ke?
Oh, okay.
Ke ada
In
spesifik?
any reaction, okay, very good question, Miss Amani. Yeah, very good question. In any reaction, there must be limiting reactant and excess, right? Excess tu kita memang sengaja bagi dia, bila kita dah tahu dia punya reaction tu, kita akan create kita punya reaction tu di mana kita supply the B in excess so that we can simplify our analysis. In the beginning, of course, you do not know. Yeah, you do not know yang the second reactant tu mungkin in excess. Ya, in excess ni siapa yang create sebenarnya? Kita. Bila kita dah tahu apa yang kita nak produce, we know the best reaction would be yang ini mesti limiting. Kalau kita nak create the situation that the A is the limiting reactant yang digunakan banyak untuk produce C, then we can manually create the initial concentration of B itu lebih banyak daripada A. Ya, in the beginning bila you create satu reaction, you tak tahu, tapi you study them, then you know. So this is the situation yang we cater untuk bantu kita to get the most optimum C or D, ya, whichever is the main product. So to answer your question, adakah applicable untuk semua? Then of course, macam saya jawab tadi, akan ada excess, akan ada limiting. How excess is that? tak semestinya 10 kali, mungkin 3 kali, 4 kali, mungkin 100 kali, something like that. Alright, do I answer your question?
Jawab,
Miss
Doktor.
Amani? Jawab. Perlu jawab.
Jawab.
Okay. Okay, through time you kena imagine benda ni ya. A chemical reaction is a very long process daripada bermacam-macam study. Whatever yang you learn in this class are the collection of established data or theories, ya. Untuk bermulanya teori ni of course, macam ni ke? Oh macam ni ke? Oh patutlah, oh macam ni rupanya. Barulah orang pun war-warkan kepada dunia. Contoh, something like that. Okay, so the theory that you learn here is based on the established theory. Yeah? So we have excess, we have limiting. It goes back to an engineer. You tahu theory, but how are you going to realize the theory practically? Oh, kita tahu misalnya ada excess, ada limiting ya. So yang mana satu limiting. So excess tadi kita nak create how excess. Dan mungkin you start eksperimen, tengok alamak dia punya production year tak banyak sangat lah. Oh, we have to make sure that excess tu lebih tinggi lagi ke. Ataupun maybe there is a scenario, tak kisahlah 5 kali ke 10 kali ke in excess, dia bagi sama je sih sebab dia dah sampai dah saturation level. Tu je dia boleh produce sebab limiting reactant dah habis. Tak kisahlah you bagi banyak-banyak pun, you punya reactor dah habis dah. Tak produce apa produk yang you nak. Something like that. Can you imagine that?
Can.
Okay? Yes, this is very important ya. Bila you buat sesuatu tu, you must understand the cerita di sebaliknya. Apa yang berlaku dalam reaktor you? Tiba-tiba bos you tanya, apa ni ruginya produce sikit je. Hilang sebelah produce lagi banyak dah beli-beli dah. Apa? Ni contoh cerita buat lawak je. Dah pergi, dah memang kaya raya dah. You tak kaya-kaya lagi. Hilang bos you lah. Contoh. Tapi you belajar chemical reaction lupa lah. Amazon aja apa tak lupa. Macam tu. So this is how you start to imagine your theory dalam satu cerita. Okay? So we are going to proceed to the next step. Once you have this one, so we are going to determine our reaction order based on the linear equation. So this is just a repetition. Now, this is where we start to analyze your collected data, yeah? The collection of concentration through time at 0 minute, 50 minute, 100 minute, and so on. So this is the concentration, the one that you see earlier. And take note of the unit, ya. Kat sini baca seperti yang which I showed just now, how you want to read it, because it's very important, ya. If you go back here, it's actually 50 times 10 to the power of minus 3 rather than 50 times 10 to the power of 3. Yeah? So it makes a huge difference. So same goes to the third column and the fourth column. So this slide shows you now mathematical punya understanding pula. We want to solve our equation here. Take note, this is our equation. We want to find our K prime, of course. We know our concentration of A to the power of alpha. So we want to find our alpha as well. And the question would be, how do we find this derivative value, dCA over dt, yeah? The change of the concentration per unit time in terms of value. So how do we find that? Yeah, this is the big question. So this is where the methods comes into picture, yeah? Let me just show you. First, before we find this value, the fourth column, we may start with the normal mathematical equation, yeah? The delta, which is the gradient. Yeah? Once you know this one, we'll go to that based on your mathematical method. We can know our derivative value by using graphical method. So I will just go to the next slide. What do you mean by graphical method? Inilah graphical method. We'll go one by one. And once we know our graphical method punya value, of course, Yeah, I will need to go to our slide lagi depan. There are 3 ways on how to determine you punya derivative value. First, either by adopting graphical method. Second, by adopting finite difference method. Or thirdly, this is again a polynomial method. Yeah, I'll have to skip to here because you have to visualize apa kita buat. Right? Take note, at different time, the derivative value for the graphical method, using graphical method, is that value, set of values. Take note, if we use finite difference, will give you that set of value. If we use polynomial method, it will give that sets of value. So let us choose one. Let us choose maybe at minute 1, minute 100 minute. With graphical method, it gives you 1.2. Finite difference, it gives you 1.24. Not so much difference, yeah? Polynomial method, it gives you 1.19. Same goes to, let's say, minute 250, 0.54. Graphical method, finite difference method, 0.48. Polynomial, 0.48. So these are just an example of different methods for you to find the derivative value. Derivative value means the change of concentration per unit time for the equation yang you wrote earlier. This equation, this one. Once you dapat solve belah kiri, of course you can solve you punya alpha and also k prime, yeah, with certain methods after that, right? So the question would be, if I go forward, which method would you adopt? Anyone? Doesn't make so much difference pun. If I have these sets of data, 3 cara berbeza, yeah, for the derivative value, when I plot this with graphical, finite, polynomial, it shows you they are almost having close values. Yeah, so it's a plot of the derivative of the CA per unit time in terms of mole per cubic decimeter per unit minute versus the concentration. Yeah, versus the concentration. So they are almost the same. Alright? So mana-mana method lah you nak pilih. Graphical ke, finite difference ke, polynomial. Doesn't matter. So now we are going to start with how does it look like if you choose graphical method? What are the things that you have to do if you choose graphical method? If someone else chooses a finite difference method, what are the equations that you must use to calculate all these points? 286, 1.24, 0.61, 0.36. Okay? If you choose polynomial, macam mana pula? So how do you get this data? So either method, mana-mana method. Alright? So since this is now it's already 11 o'clock, I think we would take our first 5 minutes break dulu before I proceed with the different methods. Is that okay?
Very okay, Doctor.
All
Doctor.
right. So let us take our first 5 minutes. Thank you, Mr. Kasha and Afsar. Okay, Assalamualaikum warahmatullahi wabarakatuh. I'm back.
Waalaikumsalam.
Ceria je. Mesti sempat pergi minum, makan semua kan. Right? So let us continue. So you see on the slide is the differential method adopting graphical way. Yeah. So how do we do that? The graphical way is done based on the first step is to write the mathematical equation there based on the formula of gradient. Yeah, gradient is difference. Yeah, banyak perkataan yang in mathematics here we use the difference between one value to the other one, or we say gradient of CA. So this is simply the gradient values, which is delta CA over delta T. Yeah, so it's simply if you compare between those two times 0 to 50 minutes, to get the gradient of the CA or the difference value is simply, of course, delta CA, ni mathematical ya, simply C2 minus C1, alright? So C2, CA2, in this case, if we are talking about A, then CA2 minus CA1, yeah? Simply 38 minus 50 over T2 minus T1, yeah? Delta T is simply T2 minus T1. So T2 minus T1 is 50 minus 0. Okay, then you'll get 2.40. Same goes, so that is why we have this reference, yeah? Same goes to the other temperature range, 50 to 100, 148, 100 to 151, 150 to 200, 0.68, then 250 to 300, 0.42. The same thing goes to here, yeah? So that would be the value of the gradients, yeah, of the concentration of A for every temperature range. Okay, so now, okay, this is written at this formula, yeah. So this is how we write the mathematical equation. Now the fourth column is the determination of the values based on the graphical method, yeah. For the values of the derivative, here is gradient. Del here is the derivative, yeah, derivative of C. Derivative of A, concentration of A per unit time. So how to get that derivative? If we were to use the graphical method, so we can use the equal area differentiation. So I'm going to go forward to this slide. The equal area differentiation technique is simply here is here suitable because simply the equal area differentiation from our previous slide can be adopted or here suitable if the independent variable are equally spaced, which is the gradient T, T1 minus T2 or T2 minus T1 or equivalently ranged. In this case, we have 50 minutes. 50 minutes. So they are equally ranged. Then you can use the equal area differentiation technique. So how does this equal area differentiation technique is done? We are going to plot our value based on the change of temperature, which is the derivative per unit time versus minute, yeah, the time. Our plan is for every time, 50, 100, 150, this is 200, yeah? 250, 300, 350. We are going to have this kind of curve whereby it uses the principle of this area, which I shaded here, is equivalent to the other area, yeah? A1, this is A1, is equivalent to A2. So this is what it means by equal area, all right? The question would be, how do we do that, yeah? This slide shows you to find the derivative value is based on the actual numerical values of the differential using the equal area differentiation based on that principle. So how do we do that? It starts with now, for example, here at 0 minute, we have 0 minute. Then we have the gradient value, which is 2.4, 0 minute to 50 minutes. So we have this range, 0 to 50. Simply make a bar graph until 2.4 here, right? Same goes to 50 to 100, 50 to 100, 1.48. So simply make a bar graph for 1.48 there. Here is 2.4, yeah? Same goes to the rest. So you get sets of bar graph, yeah, giving you the values with the height of the blue arrow there. Then using that equal area differentiation, this is a little bit tricky, yeah, but this is the theory, yeah. Having that area is equivalent to that area. So you got a point there. Same goes to here, same goes to there. Got a point there for each of the bar. Okay. Having that point, the intersection of that curve to the bar, all right? In this case, for 50 minute, 100 minute, that intersection will give you the value of the derivatives, yeah? In this case is 1.86. All right, 1.86 at 50 minute. 100 minute, 1.2. 0 minute, 3. Yeah, same goes to the rest. All right, that would be your actual value of your derivative, which is this one from graphical method. Okay. Now we're going to go to the second method, which is numerical. Numerical simply use equations. There are 3 kinds of equation for numerical using 3-point differentiation formula, the numerical method. If the point is for the initial point, then that is a formula. For interior, that is the formula. Yeah. For last point, there is the formula. Right? Adopting this method based on either starting, in between, or the last point, we'll get this equation. At initial time, we use the initial formula, initial point formula. Yeah, the actual value of the derivative, dCA over d time at t naught. Then you use this formula. So you get this value, 2.86. Right? So if we go to the last point, so T naught is this one. If we go to the last point, which is 300 minutes, we use this formula. Okay, that is fixed, yeah? Numerically, that is the formula. Simply by adopting that formula, you finally get the actual value of the derivative, which is 0.36. The rest would be the interior point formula. So if you go back to our previous slide, this would be the interior point formula. Let's say if that interior point is the third interior point, yeah? So at 0 minute is T naught. The first one after initial is T1, T2, T3. Let's say at T3, so your notation there, the subscript is 3, then simply follow that. 3 plus 1, so you got 4. 3 minus 1, you got 2. So if it's means CA4, simply follow this notation. T naught is CA naught, T1 is CA1. Yeah, in this case, CA4 is at T4. CA2 is at T2. Simply by using this formula, you can solve this value, the actual value of the derivative for the interior points. All right? And those collected value, 0.36, 0.48 minus 0.61 minus 0.84 minus 1.24 and so on, are listed in this column. All right? The finite difference column. Take note, you write as minus derivative, actual derivative value. So whatever that you write here is positive lah, based on what you write. Okay, do not make any mistakes there. That would be the finite difference. Now I want to go to the third one, the final one, polynomial values. The easiest would be you plot the data from your raw material, the raw material data, which is the concentration of A through time at different time. So simply plot that and find the equation for the plot. In this case, by using Excel, Microsoft Excel, you can conclude that from the polynomial type equation, it's a fourth order. Yeah, this is just a very fast conclusion. For example, fourth order polynomial equation. Yeah, and from here you want to find the derivative of the CA. Okay, find the derivative of the concentration of A, simply find the CA and substitute at different time because this is Y, which is CA, this is T. All right, simply derive that, then you will get the value for the derivatives at that particular point for that particular reactant. Okay, so finally you get a collection of data for the polynomial values. Do you have any question before I go to the next slide? Do you have any question? Okay, very clear, the differences of method, the graphical method, the polynomial method, and the finite difference. Yeah, it will be very tricky if you go for graphical, even though it's for this one, then you have to know the equal area differentiation, then will give you lots of errors. Then I will go for numerical method because simply following the equations and you calculate and get the values. Because it is shown that when you compare between these three methods, they are all almost the same. Yeah, the deviations is very low. The deviation between the graphical, finite, and also polynomial is quite low. Seems to be very low. Okay. It's very subjective. Yeah, it depends on the sensitivity of your reaction. Ada setengah it's very sensitive, di mana perbezaan satu pun dah besar. Dia kena beza antara satu value from the other value 0.01 baru dia kata macam tak banyak beza. Tapi kalau from one value to the other one, walaupun beza dia satu je, bukan 10, bukan 20, and that one value pun very sensitive, it can give you lots of impact. Yang tu satu pun dah kira besar. Ya, it depends. Ya, bila saya cakap tu bermaksud quite ke, very ke, it's very subjective to the situation or to the reaction, right? So from time to time, you will see this for real by yourself. Ya, ini you baru belajar teori. So I can only share my experience and tell you, but not necessarily you boleh bayang apa benda saya cakap. But I'll try my best to actually make sure that you can visualize this. Now, so we will proceed to the process data for the triphenyl methyl chloride, which reacts with methanol. And what we want to find is the K, the rate constant. The one that you see in the red box is simply the theory, yeah, having the two relationships whereby you know the derivative is equivalent to the K times the concentration of A, yeah, to the power of alpha. And of course, we have written that in terms of K prime there because tadi kita buat conclusion. This is just basic, yeah. In real, if you relate it to the real situation whereby you have A plus B produces C plus D, of course you have the effect of B and of course you have the effect of A as well at the concentration dependent terms. So now if we were to find the K, then we write, of course daripada equation sebelum saya tadi, K prime tu sebab dia ada dalam tu ada CB not yang you telah assume constant, ya. So we'll stick to this equation whereby we use the K prime A times the CA alpha, yeah, in a constant volume. The A is limiting, the B is in excess, and constant temperature. From this plot, it is found that the K value is 0.13 and the alpha is 1.99. Yeah. From this equation, you nampak kat sini ya, from this equation, actually you can rewrite that, yeah. Derivative CA over D time over CA alpha is equivalent to K prime A. All right. So you can also rewrite that, but here it's simply Y equals to MX, yeah, and plus C, right? So this is where you get the value of your rate constant, yeah, which is found to be 0.19 and your alpha is 1.99. You can simply say, dekat je dengan 2. So why not we assume it as 2, yeah? By right from the graph, it's 1.99. Yang ini yang saya maksudkan, even 0.01 pun sensitive, so you cannot simply assume terus 1 lah. So the K dia sama, ya, something like that. Here, since if we say the order is 1.99, if we want to assume the order is 2, meaning you regress lagi sekali this value from this plot and you get a new value which is instead of 0.13 now it becomes 0.122. Yeah, if you make assumption it's a second order instead of 1.99 order. All right, so that would be the value of the K prime A. Now using that, the K prime is 0.122. Let's say if we assume the beta is 1, yeah, from this assumption, when we say the B is in excess, so CB not to the power of beta, and that beta we assume to be first order, yeah, with respect to the concentration of B, it's a first order. So therefore, and it is told that the CB naught is constant. Yeah, this is the assumption that we make because it's in excess. So this is constant at and the initial concentration is actually 0.5 mole per dm cube. So from that equation, simply find K, knowing CB naught is 0.5 and K prime assuming it's second order. Tadi you dapat 1.99 tapi you nak assume second order, you get a new value 0.122. So you use that value K prime 0.122 over the initial value and finally would give you the value of the rate constant for the whole equation, which is minus RA is equivalent to the K, which is the rate constant for the whole equation with respect to both, yeah, CA alpha and CB beta. And the alpha here is assumed to be second order and beta is assumed to be first order. Okay, so That would be the value of, and finally, knowing K, knowing CA, yeah, CA, in this case, later when you know CA and then CB, then you can find the rate of reaction, the rate of the disappearance of A in the unit of mole of A disappears per unit volume per unit time. Yeah, this would be the unit for the disappearance of A. Okay. A little bit heavy because you see so many equations and so many assumptions that you have to make. So please try to reread this. If you have the textbook, please reread this. But my lecture notes would guide you which to refer. Ya, dalam textbook tu banyak dituliskan. So there are some things that we don't cover. You can read that as your extra knowledge, but of course it will help you better in your reaction engineering class, right? So that will be the end of the part 1. Then we'll go to the integral method, which is even more simplified because it's a matter of formula saja. You solve the mathematical formulas, yeah? It uses trial and error procedure to find the reaction order, and it is important to know how to generate linear plots of functions of CA versus time for 0, first and second order of the reaction. Let us start with the 0 order. Here, the key to this point is we want to know whether the reaction is 0, first atau second. How to do that? We are going to plot the CA versus time for 0 order. Why? From this proving of the derivation, yeah? With that linear line equation, we know that y is equivalent to c minus mx, yeah? C minus mx gets a straight line, yeah? Simply by plotting CA versus time for 0 order. How we get this? Of course, ini kita cakap lepas ni. Okay, I just want to show you the overall view. If it's first order, from your derivation, knowing your principle and theories, you finally conclude this equation would give you linear equation, whereby simply, this is y, this is mx, okay? Simply by plotting ln CA naught over should give, right? The second order, your final derivation giving you a straight line, only if you plot 1 over CA versus time. Okay? If you plot this one, 1 over CA versus time, you get a straight line, then you can say it's a second order. If you plot ln CA naught over CA versus time and you get a straight line, then you can say it's a first order. If you plot CA versus time, you get a straight line, then you can say it's a 0 order. The basic overview. The question would be, why for 0 order you plot CA versus time? Why for first order you plot ln CA naught over CA versus time? Why the second order you plot 1 over CA versus time? Why? Because it comes from, let us start with the 0 order. So these are the two scenarios that you know for 0 order. Yeah, 0 order means minus RA, which is the rate of disappearance of A, is equivalent to the temperature dependent terms times the concentration dependent terms, right? Let's say if you're talking about A, the A to the power of alpha. Okay, if the alpha is 0, then the whole thing is 0 order. The CA to the power of 0, this becomes 1, then it is left with the K, right? Then you have this equation. and you know the rate of reaction is equivalent to the change of the concentration per unit time. So finally, you relate those two equations, of course, for the constant volume, that would be your equation that you can use for a zero order. From that equation, you can start to solve it. Yeah, how to solve it? Yeah, you rearrange the equation. So you bring d time to RA. So you have minus dCA is equivalent to minus RAD time, right? From here, you know that minus RA is K because of the zero order. So simply substituting the equation, and to solve for this equation, you can do integration. Yeah, all right. I think this is, yeah, you can do course, you can do integration. Yeah, integrating CA naught to CA, integrating T naught to T, and you get this equation. Okay, simplify that equation, rearrange it for a linear type equation. The final equation is shown here, whereby CA is equivalent to CA naught minus KT. Okay, do you have any question? You have to try this on your own. Yeah, I write those equations on the slide, but if you don't try to write it on your own, then you tak nampak. So kena practice. Okay, please practice this. Same goes to the first order. For the first order, rate of the disappearance of A is equivalent to the temperature dependent terms times the concentration dependent terms. All right, Ca to the power of alpha. All right, or rearrange it if you want it to be positive Ra. That gives you that formula. And you know from your basic understanding, for a constant volume batch reactor, Ra is simply the change of concentration per unit time. So relate those two equations. Yeah, minus Ra, the rate of disappearance of A, is, all right, make it the same homogeneous formula, yeah, for both sides. Then, and you know, due to the first order, this rate of disappearance of A is equivalent to the power law equation, yeah? And equate that power law equation to the change of the concentration, to the change of time. And you know that alpha is 1 because you assume it's a first order, yeah, from here. So simplify that. And finally, the equation derived is that equation. So this is where you decide. This linear line equation is simply the plot of the ln CA naught over CA versus time, right? This slide is new, yeah. I think we don't have that in our previous PDF, yeah, from our lesson 1. So please take note, I will re-upload that in files. This slide is just to show you, don't get confused, don't get overwhelmed. It is just to show you the relationship of the C to the conversion, right? Meaning you kena fahamkan balik mana kita dapat equation ni, ya. We want to make a relationship between conversion and the concentration of A. Okay? It starts with this equation, so which we have derived earlier in our previous class. Simply rearranged it, and you get the final equation as CA. Same goes to here, you get a final equation of DCA. Yeah, simply substitute that in the equation here, and CA in the equation there, and finally rearrange it, integrate it, and you get another expression for the linear line equation, but in terms of conversion. This one in terms of C, yeah, in terms of C, the change of C. the concentration CA, sorry, the concentration of A. Here in terms of the conversion of A, yeah, versus time as well. You still get a straight line, but it is expressed in terms of X, yeah, the conversion of the reactant. In this case, A. Okay, not so difficult, but it's just showing you, oh, why not we plot the linear line if you want to express it in terms of conversion. So this is what you do, yeah, simply plotting that way. How do we plot that? Because it originates from your understanding. You simply re-express it. Okay. For the second order, the same thing, the same equation. Now the alpha is 2. Then simplify the equation based on your mathematical understanding. And it is shown that 1 over CA versus time will give you a linear line. So if you use integral method, scenario dia macam ni. If you use the integral method, you get a data from your lab, but you don't know whether it's 0 order, first order, or third order, whatever. So you have to make a guess. So sebab tu it says from the beginning, the integral method is a trial and error procedure. Meaning you kena teka lah. Katakan mungkin dia second order kot. So you use the principle of the second order. Second order says if you plot 1 over CA versus time, you should get a straight line. If you get a straight line, it's confirmed it's first order. The straight line of the value CA at different time, what is the CA plot? Okay, but 1 over CA lah in this case. Katakan you get a data from the lab, nak teka lah, mungkin 0 order kot. So you take the form, the understanding, 0 order says if you plot CA versus time, you should get a straight line. Paling senang you start 0 order lah sebab you got your data CA, right, versus time. So kalau dia dapat straight line, tak payahlah try first order and second order. Terus, yes, it means 0 order. Okay, meaning kalau you dapat data CA versus time, when you try 0 order but it does not give you a straight line, meaning it is not a 0 order reaction. It can be first order or second order. Right? So this is what it means by trial and error procedure. Okay, by using the integral method. We got like 2 more minutes or 5 more minutes, yeah? So basically, this is the overview of guessing your reaction order. First, you guess your reaction order. Then you get the equation. Of course, you know the equation already. You plot based on that equation, 0 order, first order, third order. If you get a straight line, then it is that order. If it's not, then try another order, right? So this is what happens. All right. Do you think you can still go on? Or you want to continue that in the next class?
Next class.
Yeah, it's quite heavy. Yeah, it's very, very heavy for today's lecture because you got so many formulas and so many theoretical understanding that you have to refresh from lesson 1 and lesson 2. Yang week 1 too very easy. Yeah, it's just a matter of the understanding of what is rate of reaction. What is temperature dependent term? What is concentration dependent terms? Week 2, it's becoming quite heavy. And of course, chapter and seterusnya tu pun, if you don't get your basic understood really well, then you get stuck when we are learning our chapter 3 or topic 3. Yeah? So I hope you take this weekend to actually reread the lecture notes and try to practice writing it on your own. Yeah, please do that. Can you do that?
Sure thing, Doctor.
All right. As said earlier, macam itulah, if we have enough time, kita bolehlah pergi breakout room, but normally no. But I'll try my best to actually plan for it. So if not, then please try on your own once you restudy the activity. You can try the kinetic challenge, and also please do your own discussion. You can make your own discussion. Yeah, you can make virtual meeting with your friends even though you are at your own home. There is no reason to say tak ada kawan nak belajar. WhatsApp pun boleh. Jom kita study sama-sama. WhatsApp lah. You dapat apa? You dapat apa? Buat. So please do that. Nah. I'll try my best to make sure that you have that opportunity to meet your friends during my class, during the breakout room. But sometimes we cannot do that. Yeah? It does not mean you tak buat. So please do that on your own. Yeah? Then only you feel happy with your reaction engineering class. Okay? All right? So I wish you all the best for this week. Week 2, we'll see again next week. Week 3. Right? Yeah, have a nice weekend and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
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 Thank you,
Thank you,
Doktor.
Doktor.
You're welcome. Bye-bye.
Bye.
Bye, doktor.
Jangan lupa
Bye.
lunch,
Assalamualaikum.
doktor.
Jangan lupa lunch juga. Ya Allah, thank you so much. Fazlika.